thing is that, remember I said that this thing is not symmetric, right? So we can actually make it symmetric, or we can define a symmetric stress tensor by multiplying the nominal stress, and we'll call this 2 pk, or let's, I guess, call it pk2. pk2. And really, I should call this pk1. So pk1, where else did I write it? pk1. So then pk2 is the nominal stress multiplied on the right by the inverse transpose of the deformation gradient. Okay. So we have, this is the second Piola Kirchhoff stress. Second Piola Kirchhoff stress. So we have that. We have this. We have this. And of course, the Cauchy stress is this symbol. Right? So we have the nominal stress, the first and second Piola Kirchhoff stress, and the Cauchy stress. They're all related to each other through the deformation gradient. And the reason that we may really prefer ultimately to solve the equation in terms of the second Piola Kirchhoff stress is that this is symmetric now. So it's symmetric. We prefer that. But in addition to that, we'll show later that it's also energy conjugate to the green strain. Right? So we can have a constitutive model that's a function of the green strain that's then, equal to the Cauchy stress, and then we can solve the equation that way. And it's symmetric, so we like that too. I'll show you later. I have plans to show you later. It's going to be easier to show, and the reason I won't do it right now is it's easier to show when you can prove that. So today I just told you the Cauchy stress is symmetric. Next time we'll prove it, okay? And when we prove it, then you can show that P2K is symmetric because this is symmetric. So if we multiply, so if we multiply here on the right by the inverse transpose, then you can show that you have basically any anti-symmetric tensor multiplied by itself will give you a symmetric tensor. So then you're going to have something symmetric, and if you already know that's symmetric, then the P2K is symmetric. I'll show you next time. PK2. How many of you are confused by all this? Yeah, it's weird, okay? I was really confused when I learned it too, okay? But here's what you got to remember. By the way, these equations are nonlinear. Even though they don't look it, they're nonlinear through the geometry, right? Because of the nature of that for large deformations or large rotations, you have nonlinearity that enters it through the geometric description. And you remember that because there's nonlinear terms in the strain, right? There's nonlinear terms in the finite strain measures. There's nonlinear terms, okay? So that's why we need all this. But the key thing to remember with these different stress measures, okay, is that, the Cauchy stress is a purely Eulerian thing. It's all in the current configuration. It relates, remember, stress just is force divided by area, right? In undergraduate stress in one dimension, it's force divided by area, right? So the force, for the Cauchy stress, the force is in the current configuration, the area is in the current configuration. It's the relationship between forces and areas in the current configuration. The first Piola Kirchhoff stress, remember, we derived it through saying that the force was still in the current configuration. We superimposed the current configuration force on the reference configuration. But then we had a reference area, right? So the first Piola-Kirchhoff stress relates forces in the current configuration to areas in the reference configuration, okay? So you have current for Cauchy, current reference for first PK. What do you think second PK is? Reference, right? So what we do really with the second PK is that we're taking the traction, the force, dF, into the reference configuration through the deformation gradient. So we're transforming the force from the current configuration back into what its image would be, its inverse map, right? What its image would be in the reference configuration, and then we have a force in the reference configuration and an area in the reference configuration. All right? Believe me, it may not seem like it, but I mean, all we're doing this for is to get to equations of polar elasticity. And the equations of polar elasticity are actually easier to understand if you understand finite deformations, okay? And so if you just linearize everything and you do everything in terms of small strain, the polar elastic equations, you have to derive them by making a lot of assumptions that may not be apparent, right? That this term is small and that term, Whereas if you just do everything in terms of finite strain, you can then linearize much easier by just looking at the nonlinear terms and saying that, well, if the deformation is small, that term goes away, that term goes away. Right? Things that you wouldn't necessarily, by intuition, know if you tried to do everything, just propose it in terms of the small strain theory, right? And ultimately, at the end of this class, we're going to write code. All that will be, I'm not going to, it's much more work. It's not necessarily hard. It's just more lines of code to implement all of this stuff correctly. And for most geomechanics settings, you don't really need to. But if you're working on sand production problems, you need this. If you're working on oil sands, like in the future, tar sands, where like imagine you're steam flooding a bitumen field in Canada. The vertical displacements can be enormous in this, right? You're steam flooding and the vertical displacements can be very, very large, on the order of meters. Imagine you're standing there when the earth just raises up a meter, several meters due to this nature. And that may be a setting where you may need to use finite deformation theory. Again, if you're dealing with casing strings or the drill string itself, there your strains may not be large in the drill string, but the deformation is large because you have a very sort of large curvature which leads to rotation, large rotation out of plane. And so there again, it's important to understand the kinematics correctly. Otherwise, you'll get the wrong answer. All right? So just not as early as I thought, but a little bit early today.